All right, everyone, welcome back to another Intro to Insect Morphology. Today we'll be covering part 23, and we're going back to the head to talk in detail about how insects see. So this will be the structure of the various types of eye lenses. And insects have multiple ways of detecting light and images. So, in the most basic form, there are eyeless insects or blind insects that can still detect light. And how they do that is called dermal reception. And it basically is, or dermal detection, or dermal photoreception. So they will have photoreceptors just embedded in their skin or underneath the cuticle is what it actually is. So, for instance, cockroaches, even if you cut off their heads, they can still detect light because cockroaches can live for quite some time without their heads, or blind cave insects, and there's quite a few that have lost their eyes over the course of evolution, can still detect light through their skin. Many insects, even those with eyes, still maintain this ability. Aphids can use the light. They have light receptors in their brain, which they can use to detect sunlight through their skin, and this helps them measure day length and stuff like that. And they can do this without their eyes. So we're not going to be going into depth with that, but we are going to be talking specifically about their eyes. So insects have three different kinds of eyes. So on an adult insect, you have their compound eyes, and this is what people are most familiar with. These are the bug eyes, as it were, and these are made up of multiple lenses. If you zoom in here, you can see that there's lots and lots of individual lenses here. And each of these lenses is called an ommatidium. So this is an ommatidium, over and over, and they're all pressed together. And these are the individual units. Plural, it's called the ommatidia, or they are called the ommatidia. Individually, it's called an ommatidium. And these are the individual lenses. Each of these lenses is a individual photoreceptor unit and has a nerve attached to the base of it, and that's how the compound eye is structured. So the insect can see not great, but they have a very, very wide angle of vision because the compound eye wraps around to the back, the back of the insect head, so they can get a very, very broad image, although they aren't very good at focusing their eyes. So they don't get a super crisp image like what we think of when we see things, but they can see a broad area around their head, and their eyes can detect movement really well because you'll have each of these lenses, it can register independently. So if something is moving across their visual field, they'll be able to detect the entire path of movement. So they can react really, really quickly to movement with their compound eyes. On top of their head, adult insects will frequently have 1 to 3 ocelli. Individually, they're called an ocellus. Plural is ocelli. And these are simple eyes that mostly detect light. In some dragonfly species, the median ocellus, which is this one, is capable of focusing and forming an image. So this is called the median ocellus, and these on top are called the lateral ocelli. So the one in the middle and the two on the sides. And these are thought to mostly help with flight. They're pretty much only found in this structure on adult insects, and they detect movement just like the compound eyes, but they're really good at detecting light, and we think it sometimes helps them orient in flying about like which way the sun is and which way is up versus down, stuff like that, so they don't fly into the ground. But they're very, very simple eyes compared to like the compound eyes. This is basically just one large lens with one large photoreceptor inside. So it's not forming complex images or detecting movement across the visual field. It doesn't wrap around to the back of the head or anything like that. They're very, very simple eyes. In immature insects, They, depending on if it's a heavy metabolist or holometabolist insect, uh, their eyes will be different. So in something like stink bugs, which the immature is a nymph, these are heavy metabolist insects. The immature is a nymph. It's basically just a small adult. It doesn't go through a metamorphosis. They will also have the compound eyes, and they will eventually. I'm not sure if all of them are born with ocelli or if they develop them later, but they add to they add ommatidia and stuff like that. They basically just get bigger eyes, but they have this compound eye structure the entire time. For holometabolous insects, ones which are larvae that then pupate and become adults, they go through a complete metamorphosis, they have a different eye structure. And what they have are called stomata, or the larval ocelli. So stomata are these. These are individual lenses, just like the ocelli. Let me get a smaller brush here. So it's an individual lens with an individual, that each act as individual photoreceptor units. They are generally multiple. There are some larval insects that cannot see. They don't have stomata, but most larval insects do. So for instance, flies rarely have stomata. Most wasps and bees don't have stomata. But things like beetles, caterpillars, sawflies, neuroptera larvae and stuff will have stomata. They can see somewhat. These have a similar structure to the ocelli, but it is a different structure. They are not analogous, or rather, they are not homologous with the ocelli. So they do have a different structure. They only have them during the larval stage, and then it breaks down and they form their compound eyes during pupation into adulthood. These are also very simple lenses. They're not great at forming images. And because, unlike a compound eye, they are very, very limited on how much of the head is covered. Frequently, like caterpillars, when you see them on leaves, they will bank their heads back and forth, and it's so that they can get a bigger range of vision. Although they do have pretty terrible vision. So we're going to go through all of the eye structures. We're just going to do a quick couple drawings of cross sections of each of these eye structures. And we're going to start with I think we're going to start with the stomata. This is by far the simplest structure, and then we'll work up to the compound eyes. So let's get a blank page here. So yeah, stomata. So we'll do this. So the stomata again are these larval eyes. So what does a larval eye look like in cross section, and what makes it different than an ocellus? So on top you'll have a large lens. So this is a corneal lens. So this is the cornea. You'll have a large corneal lens which light passes into. And below that, you have a secondary lens called the crystal lens. This is crystal lens, which again will help focus the light. Ocelli don't have this crystal lens. And below that, you have the photoreceptive structure. Let's turn this to black. Called the rhabdome. Black is rhabdome. And this is actually where the light strikes. It comes in and strikes this rhabdome through the lenses. And around that rhabdome, you have a series of nerve cells called the retinula. So that's the rhabdome. And these are the retinula. And these are nerves. Retinula nerve cells. And you'll have around that, like all eyes do, you'll have some pigment. So let's change to blue. Blue. And then on the sides of all of this, you'll have pigment. So what will happen is that the light comes through the eye through the lens, through the secondary pair of crystal lenses, and strikes the rhabdome. The rhabdome becomes distorted from its interaction with the light. It becomes energized, it becomes distorted. It causes, the light coming in will cause distortions in the pigment cells because the pigment can absorb some wavelengths of light and can't absorb others. And it causes an electric current to be generated in the retinula cells. These are the nerve cells. And that will go to the brain. So that is how, and that is as much as the stomata can do. It can't get good angles or anything like that. It's literally just picking up shadow and light changes, very, very simple images, and then processing it directly to the brain. So for something like the ocelli, they're a little different, slightly more complex, but it's a similar structure. So again, you start off with a large lens. This is a corneal lens. So this is the cornea, and the light will be coming in here. And then you'll have a vitreous layer underneath, kind of a gap, and then below that you'll have the retina, which is really just a collection of the retinula cells and the rhabdomes. So you'll have a bunch of cells underneath this lens. So it's more complex. It's not just one individual rhabdome and a couple retinula cells. It's a bunch of rhabdomes and a bunch of retinula cells. So this central point here is the rhabdome, and around it are the retinula. And if you will remember, the retinula are the nerves. And again, you'll have some collection of pigment. I always turn this on to the wrong color. You'll have some collection of pigment around this structure, right? So this is pigment. So you have all of these rhabdomes. The light comes in and strikes the rhabdomes. The rhabdomes become distorted. Some of the pigment absorbs some of the light. That becomes distorted. And charge is generated in the retinula. All of these retinula have interneurons coming off of them, and it feeds into one big neuron. So this would be the ocellar nerve. And that goes to the brain. So this, you have a lens. Light percolates through the lens, percolates through the vitreous layer, this gap, this fluid gap, strikes the rhabdome, generates a charge across the retinula cells. So that's, let's do that like this. Bzz, bzz. And that charge then gets condensed across all these rhabdomes and retinula cells and feeds into one giant nerve, the ocellar nerve, that then goes to the brain. So compared to something like the stomata, there's more going on. You have more rhabdomes, you have more retinula cells, you have a broader lens that forms the cornea. You don't have this crystal lens in the middle. You have a broader area of pigment around the sides. So you get more of a signal, more of a visual signal from the ocelli than you do the stomata. And then finally, you have the compound eye ommatidia. Let me change this to black. So if you will remember, the ommatidia on the compound eye, it's not just one thing. You have all of these lenses on a compound eye. Each of those lenses is called an ommatidium, and each of them is an independent visual unit. So we don't need to talk about the whole compound eye. What we need to do is talk about the individual units, because once you understand how one unit works, then you just replicate that 1,000 times across the scope of the compound eye, and you get that's how you form the eye. So with an ommatidium, you have, ommatidium, the M is for singular. You have a corneal lens. So you have a lens. This is the cornea. But underneath that, you have like with the stomata, you have a crystal cone, and around that you have pigment cells. You have primary and secondary pigment cells. So let me get my blue for that, since that's what I've been using. So these are pigment cells. And then beneath that, you have our friend, the rhabdome again. So this rhabdome is in all of the ocular structures. You have the rhabdome, and around the rhabdome, you have the retinula cells. So the center part is the rhabdome. This is the photoreceptive structure, and then these cells on the side are the retinula cells. Then these are the nerves. So again, what do you have coming down? You have, I always forget to change this to yellow. You have the light coming in through the lens, goes to the secondary crystal lens, strikes the retinula or strikes the rhabdome, and the pigment cells. Those interact with the light and form a charge across the retinula cells, and then that will be connected to a nerve coming out the bottom. Each of these has a nerve coming out the bottom. So it's not just two retinula cells in this case. It is what would be 1, 2, 3, 4, 8. So how this would be set up is you would have the rhabdome is actually kind of, this is a cross section in the other direction. You have a rhabdome that is kind of 8-sided. You have that central rhabdome, and then each of these is a retinula. So these are the retinula, and this central portion is the rhabdome. So that's the basic structure of the eye. They are not super complex in that, like, compared to mammalian eyes and some or stuff like that, they're not super complex. They are not great at seeing, but they do tend to pick up more wavelengths of light. So like honeybees can see in ultraviolet. Generally speaking, insect visual wavelengths are ultraviolet shifted. So many insects can't see red or infrared, but they can see into the ultraviolet spectrum. So they can kind of see orange and yellow, and then it goes all the way through violet to ultraviolet. Many insects can also see polarized light based off of how the light comes in across the compound eye. So if it's coming in from certain directions, it's polarized in certain directions, they can detect changes in polarized light. So like honeybees can use polarized light for navigation as the sun moves and the polarity shifts, or rather the direction of the light shifts. So they also, because they have all of these individual units, they can react extremely fast to movement. They have a much faster reaction time than people or other mammals. So that's the basic structure of the insect eye, and I'll talk to you guys later.